So we've gone through a couple of examples of constructing decision trees, both manually, just by eyeballing it, and then using scikit-learn to generate decision trees. But let's actually look at an algorithm for generating a decision tree. So we want to avoid overfitting, right? So let's first look at how we create decision trees by looking at the data. So this is going to be just a traditional decision tree generation algorithm. So we're going to start with all of the data in the root node. And then we're going to repeat the process until either every node is pure or it's unsplittable. And I'll define what that means in just a moment. So we're going to pick the best feature, x, and then we're going to pick the best split value, beta. So for example, we could say x is the petal length and beta is a length of 2. Then we're going to split the data into two nodes where one is x, that feature, less than beta, and the other is where x is greater than or equal to beta. Now, definition. So we say that a node is pure if it only has one type, so one class. Then that node is considered pure. A node that has duplicate data that cannot be split, so from two different or three different or more classes, is called unsplittable. So those are the two terminal nodes that we'll have. Either all of one class or there's no feature that we can use to split that node into pure nodes. Okay, so of course, if we're going to have to split on a feature, the question is, what is the feature that which gives us the best split? And what should be the value, the split value associated with that feature? So equivalently, the other way to think about this is if we're looking in 2 dimensions, it would be, so petal width and petal length, what horizontal or vertical line do we want to draw? So now we start with our root node contains 50 setosa, 50 versicolor, and 50 virginica. So what is going to be our split feature? And what's going to be the value? So where on the horizontal axis are we going to draw a vertical line, or where on the vertical axis are we going to draw a horizontal line? So that'll define which feature we're going to use and which split value we're going to use for that. So for example, we could say we're going to split on width greater than 1.5. So that would yield in the left node 50 setosa, 46 versicolor, and 3 virginica. And on the right, it would yield 0 setosa and 4 versicolor and 47 virginica. So is that good or not? Right? It does help, right? We've eliminated all of the setosa from the right node. So that's reduced the number of classes, but we don't have a pure class on the left and we don't have a pure class on the right. So maybe we could do better. So what if we did a vertical line at petal length greater than 4? Okay, so now we would end up with, on the left, 50 setosa, 9 versicolor, and 0 virginica. So we've eliminated one class. There's no virginica on the left. But on the right, we've also eliminated one class. So there's no setosa, but there's 41 versicolor and 50 virginica. So is that better than what we had before? Right? And so what if we instead said the petal width greater than 0.5? Okay, so now on the left we have 2 setosa and 50 versicolor and 50 virginica. But on the right, we have 48 setosa. So we have a pure node. So is that better than the other choices? So we can just keep drawing lines like this. But really what we want is some sort of rigorous definition for what is a good split that we can use to compare those 3 splits or additional splits. So the rigorous definition that we're going to use is node entropy. So node entropy is defined as follows. So we're going to say that P sub C is the proportion of data points in a node with label C. So the node at the top of the tree, in this case, has P sub 0. There's 34 out of the 110 in that node, so it's 0.31. And then P sub 1, there's 36, so that would be 36 out of 110, or 0.33. And then there's 40 of the second class, so P sub 2, and so that'll be 40 out of 110, or 0.36. So, given P sub C, we're going to define node entropy as follows. So it's going to be the sum of each of the P sub C values times the log base 2 of that P sub C value. Now, since P sub C is less than 0, the log base 2 is going to be a negative number, and so when we take that sum, we're actually going to take the negative of that, so we get a positive number out of this. So we end up with negative 0.31 times the log base 2 of 0.31 minus 0.33 times the log of 0.33 minus 0.36 times the log of 0.36. So we end up with 1.58 as our node entropy. So this is entropy, it looks like cross entropy. It comes as expected from information theory. And so this gives us an idea of basically how unpredictable or uncertain a node is, right? And we'll see as we look at different types of groups of species or classes per node, how that affects the entropy. And that'll help give you a better understanding of how we can use the entropy. Okay, so let's try a little question. So what is P sub 0 in this case, right? And what is the entropy of the node on the left with 31, 4, and 1 in each class? So try writing out an expression or actually computing an exact value. So pause the video and then work through it. So again, determine what P sub 0 is and then write out an expression for the node on the left, the node in orange. Okay. So what did you come up with? Well, P sub 0 is going to be 31 out of the 36 nodes, 36 elements that are in that node. So P sub 0 is going to be 0.86. What about P sub 1? Well, it's going to be 4 out of 36, or 0.11. What about P sub 2? It's going to be just 1 out of 36, or 0.028. Okay, so now our entropy, S, is going to be each of those P sub C's times the log of the P sub C value. We end up with an entropy node entropy of 0.68. So again, we can think of the entropy as how predictable or unpredictable our node is. If we have low entropy, that means our node is more predictable. If we have high entropy, it means our node is more unpredictable. So we want low entropy. So we start with entropy 1.58. With this split, on the left, we've dropped our entropy down to 0.68. So we've added more predictability. So let's explore the entropy. And we can make some observations about the entropy, right? A node where all of the data are part of the same class is going to end up with 0 entropy. And that's just because the log of 1 is 0. So, on the other hand, if we have data evenly split between two classes, it's going to have entropy 1, right? Because it'll be the log base 2 of 0.5 times negative 0.5 minus 0.5 times the log base 2 of 0.5. So we end up with just 1. All right, so all the same class, 0, equally split 1. What about if we have multiple classes? What will we end up with? Well, if we had 3 classes, we'd end up with entropy 1.58. The logs don't work out as nicely, but you can see the entropy is going up. As we have more and more classes, that's going to be more unpredictability for that particular node. Now, a node where we have the data split into C classes is going to have entropy log base 2 C. Okay, so now we can use weighted entropy as a loss function. And so weighted entropy is going to be the loss function that's going to help us decide which split to take. So let's say a given split is going to result into 2 nodes, right? Each of those nodes is going to have an entropy associated with it, right? And so what we're going to say is that given 2 nodes, X and Y, with N1 and N2 total samples, the loss will be given by N1 times our S function for X plus N sub 2 times our S function for Y over the sum, the total number of samples, so N1 plus N2. So let's see what that looks like in practice with an example. So our first split choice with width greater than 1.5. Let's compute the entropy of the child nodes here. So the entropy of our node on the left with our split 50, 40, 46, and 3 is going to be 1.16. The entropy of our node on the right with 0, 4, and 47 is going to be 0.4. So the weighted average will be 99 over 150 times our 1.16, that's on the left, and on the right we have 51 nodes, so 51 over our 150 times 0.4. So we end up with a weighted entropy of 0.9. Okay, what about for the split number 2? Well, here on the left it's going to be 0.62, and on the right it's going to be 0.99, and our weighted average ends up being 0.84. So again, if we go back to our last one, our first split was 0.9, our second split ends up at 0.84. So we're doing better than our first choice. So between the 2 choices, if I had to make a choice, I would choose the second split. But we did more, so let's look at the next one. So if we look at choice 3, where our width is greater than 0.5, our entropy on the left is 1.12, our entropy on the right is 0. And so our weighted average is 0.76. And so that's better than split choice number 2. But what would happen if we just move that horizontal line up a little bit so we captured all of the setosa with that on the right? And so that would be if we set the width to 0.9. So now the entropy of our node on the left, where we just have or on the right rather, where we have 2 classes equally split, is going to be 1. And on the left, where it's a pure node, everything is in 1 class, our entropy is 0. And so our weighted average rather for our loss function is going to be 0.66. So that's even lower than split choice number 3. So of all of the choices, this would be the best choice. So now you can see how this will translate into an algorithm that we'll use for generating decision trees. Okay, so again, we start with all of the data in the root node, and then we're going to repeat the process until every node in our tree is either pure or unsplittable. We'll pick the best feature X and split value beta such that the loss of the resulting split, our weighted entropy, is minimized, right? And then we'll split the data into 2 nodes, one where X is less than beta and the other where X is greater than or equal to beta. Again, pure means that only 1 class. Unsplittable means multiple classes, but there's no feature we can use to differentiate them. So now that we have a decision tree generation algorithm, we can take a look at overfitting.